Section 7.2, inverse transform and transforms of derivatives. We're going to look at the inverse problems, which is the first part, or using the script L, superscript -1 to represent the inverse Laplace transform operator. The second part of the package, we're going to look at the transform of the derivatives and use the Laplace transform to solve the linear differential equation. The function f of s represents the Laplace transform of the function f of t, or in the notation, the script L of the ft equals f of s. Then the f of t is the inverse Laplace transform of the function f of s. Or we write in a notation that the f of t is the notation L superscript -1 of the fs. The theorems that you saw in 7.1, that's about the Laplace transform of the function in t. For example, the first one, the Laplace of the constant 1 is 1 over s. The Laplace of t to the power n is n factorial over s to the power n plus 1. The Laplace of e to the power at is 1 over s minus a, and so forth. And this time we're going to do it backwards as by the inverse Laplace of 1 over s to become the constant 1. The inverse Laplace of n factorial over s to the power n plus 1 is t to the power n, or the inverse Laplace of 1 over s minus a is e to the power at. So we are going to recognize the pattern of the expression in s. Let's see if we can apply which theorem to find the inverse Laplace transform. And the inverse Laplace transform operator is also the linear operator. Inverse Laplace of the sum is the sum of the two inverse Laplace transforms. The first example, we are going to find the inverse Laplace transform of 1 over s to the power 4, as we recognize this as 1 over s to the power of some form the n as a theorem. It's similar to the pattern of t to the n equals the inverse Laplace of n factorial over s to the power n plus 1. We are going to adjust the expression in s as s to the fourth is s to the power 3 plus 1. And this case, we can see as n equals 3. To make it or to adjust it to fit into the inverse Laplace transform formula, we're going to need to multiply the numerator and denominator by 3 factorial. And then rewrite it as the inverse Laplace of 1 over 3 factorial multiplied by 3 factorial over s to the power 3 plus 1. For the coefficient 1 over 3 factorial, that's a constant multiple, so we can take it outside of the inverse Laplace notation. And the 3 factorial over s to the power 3 plus 1, the inverse Laplace of this is t to the power 3 with the coefficient 1 over 6, which is from 1 over 3 factorial. So then the inverse Laplace of 1 over s to the fourth is 1 over 6 multiplied by t to the third. The next example, we are going to find the inverse Laplace of 1 over 3s plus 1. First of all, we're going to make the coefficient of the s to be 1. We write it as 1 over 3 multiplied by s plus 1 over 3. And then the 1 over 3 here is the coefficient. Take it outside of the operator. Now we have the inverse Laplace of 1 over s plus 1 over 3. And also recall the Laplace transform of e to the power at is 1 over s minus a. That means e to the at is the inverse Laplace of 1 over s minus a. We're going to rewrite the denominator as s minus the quantity, and this quantity is negative 1 over 3. Therefore, we can see a as negative 1 over 3, and then apply the theorem to get 1 over 3 multiplied by e to the power negative 1 over 3t. Next example, we are going to find the inverse Laplace of the numerator as s plus 2 to the power 2 divided by s to the third. First, we're going to expand the numerator as s plus 2 squared is s squared plus 4s plus 4 and all divided by s to the third. And now we're going to expand them, write it as 1 by 1 term. So s to the second over s to the third becomes 1 over s. Second term becomes 4 over s to the second. And the last term becomes 4 over s to the third. As the inverse transform has the linear property, so we can rewrite it as the sum of 3 inverse Laplace transforms. The first one is the inverse Laplace of 1 over s. The second one, as for the constant, so going to take 4 out of the operator. And then inside is just 1 over s to the second, similar to the last one, which is 1 over s to the third. As we see this, the result going to come out as the polynomial. But the first one is the Laplace of 1. Let's make a note on the side here. The Laplace of the constant 1 is 1 over s. The Laplace of t to the power n is n factorial over s to the power n plus 1. That's what we're going to apply for this problem. So the first going to give the result as 1. The second, we have 1 over s to the second. Identify this as s to the power 1 plus 1. Therefore, the n equals 1. We need to multiply top and bottom by 1 factorial, which is the same as the original term. So no change for this. Then the second term, the inverse Laplace of it is t to the power 1 or just t multiplied by 4. And the last one, s to the power 3 is s to the power 2 plus 1 or n equals 2. And as n equals 2, we multiply the numerator and denominator by 2 factorial. And this is the same as 1 over 2 factorial multiplied by 2 factorial over s to the 2 plus 1. 1 over 2 factorial can be outside to join the number 4. Becomes 1 over 4 multiplied by 1 over 2. And the inverse Laplace of 2 factorial over s to the power 2 plus 1. So the last Laplace transform will give us t to the power second and multiplied by 2 added by the first two terms that already came out. So this is the inverse Laplace of the quantity s plus 2 squared over s to the third. In this example, we are going to find the inverse Laplace of 1 over s to the second plus 2. On the side notes, the Laplace of the cosine of the kt is s over s squared plus k squared. The Laplace of the sine of kt is k over s squared plus k squared. S is the variable, k is the constant. For our case, we have the pattern of s squared plus the number, and the numerator is the constant. So we're gonna work on adjusting the form to fit with the way that we can apply the Laplace of the sine of the kt. Rewrite the denominator as s squared plus the number squared. The 2 is the same as square root 2 squared. This way, we can identify k as square root 2. Then, as k equals square root 2, we're going to need to multiply or make the numerator to be square root 2. So then multiply the top and bottom by square root 2. The inverse Laplace transform will be adjusted to be 1 over square root 2 multiplied by square root 2 over s squared plus square root 2 squared. And the constant will come outside, becomes 1 over square root 2, the inverse Laplace of square root 2 over s squared plus square root 2 squared. And this will give us 1 over square root 2 multiplied by psi of the k, which is square root 2 times t. And this is the inverse Laplace of 1 over s squared plus 2. The last example, we are going to find the inverse Laplace of 1 over s squared plus s minus 20. This time, the denominator has 3 terms. We're going to start with factoring the denominator to get 1 over s plus 5 multiplied by s minus 4. On the side note, we are going to find the partial fractions. So we write it 1 over the quantity s plus 5 multiplied by s minus 4 as the sum of 2 partial fractions. The first one with the denominator s plus 5, the second one with the denominator s minus 4, with the numerator as a constant a and b. We're going to find the value a and b. If these two expressions are equal, that means we can rewrite the denominator on the right hand side as a common denominator as the s plus 5 multiplied by s minus 4, and the numerator becomes a multiplied by s minus 4 plus b times s plus 5 equals 1 over s plus 5 multiplied by s minus 4. And now we can equate 1 with the a multiplied by s minus 4 plus b times s plus 5. To find a and b, pick the convenient number like s equals 4. If s equals 4, we have 1 equals 9 times b, or the value b is 1 over 9. For s equals negative 5, we have 1 equals negative 9 times a, or a equals negative 1 over 9. Now we have the two fractions as negative 1 over 9 divided by s plus 5 plus 1 over 9 divided by s minus 4. With the linear transform property, we can rewrite this as a sum of the two inverse Laplace transform with the constant multiple. The first term will become negative 1 over 9, the inverse Laplace of 1 over s plus 5. The second one becomes 1 over 9 multiplied by the inverse Laplace of 1 over s minus 4. And from the theorem, the Laplace transform of e to the power at is 1 over s minus a, or e to the power at equals the inverse Laplace of 1 over s minus a. From this theorem, we can see the first fraction, the a is negative 5, and the second one, the a equals 4. Now we can see this as a result of negative 1 over 9 multiplied by e to the power negative 5t, with the second term as 1 over 9 e to the power 4t as the inverse Laplace transform of 1 over s squared plus s minus 20.